Okay. Okay, it needs to be changed. Sorry about that. Perfect. Welcome back, everybody. So this should be lecture 14. So as I said, this should be lecture 14. And we want to continue talking about digital side channels. So last lecture, we start with what side channel is, and we said that generally side channel refers to any unintentional activity that a competing device creates. There are multiple different options, including electromagnetic, power, time, etc., etc. We said that there are essentially two types of side channels. There's digital side channels and there's physical side channels. And for now, we're going to focus more on the digital aspects of side channels. We basically said that digital side channels is caused by the fact that we are sharing this exact same hardware between multiple processes. And because you are physically sharing the same hardware, the chance that an adversary can break the isolation that we assume that exists in, excuse me, that exists between processes basically breaks. So as I said before, we are kind of assuming that in memory we have different processes, and then we cannot really access from process number 1 to process number 2. But since we are sharing this on the same, hardware, the same physical chip, we will show that there are some physical characteristics of this, for example, process that propagates through this process, and this process can read that. Okay, so if you were actually physically, divide these two from each other using two separate, for example, memory chip, or using two separate hardware, then there wouldn't be any digital side channels. Okay, so we want to talk about how, and in order to understand how this works, basically this is usually a contention base, which what this means is one process understand the activity of the other process based off the contention that happens between these two. So we're going to talk about that. Specifically, we're going to talk about contention in cache. And in order to understand that, we kind of need to get a detour and just very quickly talk about the memory hierarchy and cache design. So we talked about memory hierarchy, and we said that essentially memory hierarchy is kind of shaped like this, that if it's smaller, it's faster, and if it's bigger, it's slower. And what we need to do is kind of like hide the delay of this side, this bottom side, by having levels of memory, and then tries to store things in each level. And if you're smart about the way that we are storing things, then majority of the time you are only talking to this smallest but fastest cache. And it's kind of like becomes the delay that we see from the CPU side becomes a weighted average of the delay of accessing these multiple different levels. And if the majority of time you are basically accessing this fastest part of the memory, it virtually feels like that the virtual delay of your memory is basically mostly this one. Have a question? So that's generally the idea and the motivation of using a cache. So what we want to show to you is one specific structure of the cache called set associative. Before that, let me actually just So basically the cache is smaller memory, smaller portion of the memory. So usually this size is much, much smaller than this size. Give me a second. For some reason, my pen doesn't work well. It's going to be better. Maybe not. Anyway, so this would be our main memory. You can't see it. Oh, you can't see it? I'm sorry about that. So this would be your main memory, and this would be your cache. And obviously, since your cache is much, much smaller than your main memory, you only can, store a portion of the memory, right? So for example, you can only store this portion of the memory, okay? So in order to know what you have stored and what you didn't store, you need a mechanism to kind of like, when the address comes in, you need to know whether this exists in a cache or not. In order to do that, what we usually do is that if the address coming from the processor, okay, we typically divide this address. Let's say this is a 64-bit address. We divide this into two pieces, a tag and an index, okay? So the tag is basically just saying, what is this address? What is the name of this address, okay? And the index is basically just indexing this table, okay? So the way this works is that, let's say we have 4 different indexes, right? So log of this number of contents would be the bits for the index, right? So 2, for example. Since we have only 4 contents, we only need 2 bits to address this, right? And the rest of the address, whatever that number is, would be the tag that we need to store in the cache. So for example, if you have a 64-bit address and you have only 4 contents, 4 available, row in your cache, what you need to store is 64 minus 2 bits of tags, which is 62 bits of tags. You need to store 62 bits of tag in each of these lines. Why you need to do that? Because when a new address comes in, use the lowest 2 bits to find which index you have to go, and the rest of the bits you need to check to understand whether you have what address you have stored, right? Because there are multiple lines in this main memory that maps into the same index, right? So you need to store what you have. You need to remember what you have stored. So you need to first check the tag, okay? And of course, if you add more indices, if you add more content in your cache, then you need to store lower amount of tag, okay? And in the extreme case, if your main memory is the same size of your cache, you don't need to store any tag, right? So that's something very basic and simple. And of course, your cache needs to also store the actual data itself, right? So you just don't want to store only the tag. You also need to store the data. So in reality, your cache is a structure like this, that it has 2 tables. Let's say still we are doing 4. 1, 2, 3, 4. There is one that we call tag store, and there's another one that we call data store. So tag store is only storing the tag value. Data store is actually storing the actual content of that memory line, right? So this tag part is just to tell us what we have stored in this cache. And once we found that, okay, there is this specific address that is being stored in the cache, then we go to the same index in the data store and we actually bring the content, okay? So let me give you an example. Let's say the CPU wants to do load maybe address 0x100. And in this case, what we should do is that this address goes into the memory, goes into our cache, and we first use the first 2 bits, which in this case would be 0, 0. We go to the index of 0, 0 in our 4-entry cache. And then we check the content of the tag. So basically, for example, if you have 64 bits, we have to calculate what the tag is. And then we're going to compare this tag with the tag that we have stored here. All right. We're going to compare these. If it's a match, we're going to say it's a cache hit. Then it means that we actually have this value stored in our cache. So we go to the data store and we bring the data. And this way we're kind of saving a trip to the main memory. So we have the data stored in the cache. If it's not equal to the tag, these 2 tags are not equal, then we said that this is a miss. And we need to go to the main memory to bring the data. Okay, so that's the way that the cache operates. Yeah.
So the tag's only purpose is just to check if the data is valid or not.
Yeah, to know that whether we have stored this or not. Remember, because the size of the main memory is much bigger than the size of the cache. So not all the addresses are stored in the cache anyway, right? So we first need to know whether we have stored this address already or not. If yes, then we go and bring the data.
Okay, I have one more question. When we say the cache, do we mean like it's on the CPU, or if it's not in the main memory?
So remember, the cache hierarchy has multiple levels, and this is basically the story of every level. So we start with L1. If it's not in L1, we go to L2, we go to L3, and then we go to the main memory.
Where are L1, L2, and L3 stored?
So they're stored usually in the same system, on the same chip with the processor. So the processor is, so usually these days we have something like, let me actually draw it here. So we typically have a complex chip that the majority part of it is the core logic of the CPU, and then the rest of it is, for example, L1, L2, and so on and so forth. Usually L1 and L2 is on chip, and L3 is usually outside. But it really depends on the technology.
Thank you.
How does the cache ensure that like you don't just end up? How does it ensure that the index is normally distributed or uniformly distributed?
So for the index, we usually use the lower bits of the address. Okay, so a new address comes in.
Isn't that likely to end in 0 or 8 or some other like multiple of, I guess, 8 or 4 or 8 more often than other numbers?
Oh no, to your address, usually, I mean, your workload might not be equally distributed. Sure, that's one issue, but your cache is usually distributed. And one thing that I didn't mention is that you don't store 1 byte in your cache. You typically store 64 bytes in one line of your cache. So when you're addressing your consecutive, for example, array values in your code, let's say each one is 1 byte. From 0 to 63, you're always accessing the same cache line, and that way you get lots of hits basically because of that. So the size of the cache, the content, like how many bytes you're storing here, that could be more than 1 byte, and that's usually 64 bytes actually. But you cannot guarantee that you equally distribute your data stored in this cache, and actually that's a known problem. That you never know that whether maybe your workload is designed such that all the addresses map into the first line of the cache, and that leads to a poor performance. But since you are using your cache for multiple cores and multiple applications, the chances that this is randomly distributed is pretty high. Any other questions? So this is the story of the cache. How many indexes should we use, and what is the size of the index? What is the size of the tag store? Is a story that if you are more interested, you have to look deeper into a computer architecture course. But the popular one that's usually these days are being used is what's called a set associative cache, which the idea is that, remember we have the tag store and data store. So what we do is that instead of having one tag store and one data store, what we do is we are saying that we are basically having multiple what's called ways, which essentially we have multiple of these tag stores and multiple of these data store. And we repeat this for each index. And basically what we do is we are saying that all of these are mapped into the same index. Okay. So how does this help? It helps for the scenario that you just mentioned, that if two addresses happens to be on the same index, they don't fight for the same place because, for example, we have a replicate of 4 different possible storage for the same index. So this way, all of them can share the same index together, and this kind of like help us to improve our hit rate. Well, this of course comes with the area storage overhead, but you can always remove some of the indices and add more of these replicates. Okay, so the difference between what I described here and what you see here is that instead of having only one tag store and one data store, for every index we have multiple of these tag store and multiple of these data stores. All right. So how do we know what we have stored? So basically, similar idea that I described here, it's going to be here. So first, let's say your address is, in this case, 8 bits. We're going to divide this address into 2 pieces, the index and the tag, same as before. Let's say your cache has 8 entries in this case. So we need log of 8, which is 3 bits. So we need 3 bits of index. And remember, here we have 2 copies of the same index. So we have 2 tag stores and we have 2 data stores. So what we're going to do is we're going to get the index. And let's say in this case, the index is equal to 111, which means that we have to go all the way to the last line of the cache. And since we have 2 copies, 2 possible entries for the same index, we need to compare this tag with both of these entries. So because we never know which one you have stored, we need to compare with both of them. And if the results of any of these 2 is correct, we call it a hit, right? So the chances that we have a hit now, it's twice as if we had only 1. And if it's a hit, then we're going to go to the corresponding data store table. For example, if this is a hit, we're going to go here. If this is a hit, we're going to go here. We're going to bring the data, and we have the data that. Okay, this is the story of what's called a set associative cache, and you might have multiple of these tag store. Okay, we typically call these bays. All right, so for example, this is a 2-way set associative. All right, if you have 4 of these, we call it 4-way set associative. And set associative is the most commonly used structure for the cache. It's not the only way of structuring the cache, but typically this is the most common way of storing your data in cache. Okay. In normal processors, typically we have either 8 or 16-way set associative. That's the normal number that we use these days. Okay. Any questions about the cache? So you're gonna see how this set associative can help us with why this is relevant to the security problem. The second thing that you need to understand is going back to virtual to physical address that we have already extensively talked about. If you remember, we said that essentially we need to have a set of virtual addresses when we are dealing with the processor. And when we are actually accessing the cache, we need to translate it in a real physical address. And we said that this is actually happened in a page table. So any access to the memory has to first be translated. And after it's translated, it's actually now we have time to go and access the cache or access the memory. So basically, if you look at the access timeline, processor, let's say processor 1, issue a load for a store. Then, so let's say issue a load to address A. Then operating system usually translates virtual A to physical A. So let's say call it this call this one PA. Then we need to go to the main memory or the cache and bring access PA. And then we bring back data to the operating system, then we bring back the data to the PA, right? So there is a translation first, and then there is the actual access, okay? But the problem with this is that this virtual to physical address translation needs to access the page table, right? And page table itself is an array, right, in some sense. And where do we store the page table itself? We store the page table into the memory, okay? So there is page table itself is quite big, so we need to store this into the memory, okay? So what happens is that if you want to load something, we have to first issue one load to the main memory to do the translation, and another load to the main memory to access the cache. So every access to the memory is basically two accesses in real world, because we need one access for address translation, another access for the memory access, right? And this is not great because we are essentially saying that the delay for accessing the memory is twice as what we have thought it was, okay? So what we can do, the solution for this is that, what about storing these page tables into a cache? So a similar way that we store the content in the cache, how about we store the page table in the cache as well? And of course, since the page table is so big, you cannot store everything in the cache. So you need to kind of like selectively store things from your page table into your cache, okay? This is what's called a specialized, cache called translation look-aside buffer, or TLB. So TLB is nothing different than a normal cache. The only difference is that instead of storing the content of the memory, it's storing the virtual to physical address translation. And as I said, the page table is usually very small, so it cannot store all the addresses. It can only store a subset of addresses. And in order to intelligently save those, we need to come up with strategies of what is the most frequently used addresses that have been translated, and let's actually store those. Okay, so basically the way it works is if you want to do the address translation, this is the virtual address. What we usually do is that we first ask the TLB to see if it has the translation for this virtual address already. If it has it, actually, if it has it, then we don't need to go to the main memory to read the page table. If it doesn't have it, then we go back to the story that we just told you, that we need to go to the page table first. That's one access. We bring back the physical address. Then we go to another main memory and then do the second access, right? But if the majority of the time there is a TLB hit, then we don't need to be worried about the first access. So basically, we are going back to just only one access per memory. Does that make sense? Okay. So two things that I wanted to share with you: the cache and the page table. The final thing is about the disk. If you remember, I said that we have our CPU, we have our caches, we have our main memory, and then there's usually a bigger storage, which is the disk. And we said that the disk is much, much bigger than the main memory, but much, much slower than both main memory and the cache, okay? So how do we deal with the disk? Dealing with the disk is basically using this, this idea of what's called the demand paging. So in CPU's world, disk is not different than the main memory. The operating system creates, the operating system creates a virtualized environment in some sense that from the CPU perspective, main memory and disk is just a large consecutive memory together. And whenever we need to access something, operating system brings those pages from the disk to the main memory, okay? And it's the operating system job to make sure that we always have all the pages that we want in the main memory. Of course, this wouldn't be the case always. There will be some scenarios that we need a specific page that is not in the main memory, but it's in the disk. And in this case, we call it a page fault, that the page does not exist in the main memory. We have to wait for the operating system to actually go into the disk, bring that data to the main memory, and then we need to access that value. And that's a huge delay, but if the operating system is smart by selecting what to store in the main memory and what to store in the disk, the majority of the time, we are accessing only the main memory, right? So disk, in other words, is just an extension of the main memory, and the operating system is the ones that handles what we need to store in the main memory and what we need to store in the disk. And we usually call this a demand paging. Based on the demand of the page that we want, the operating system decides what to store where, okay? Any question here? So as I said, since of course the main memory is smaller part of the disk, similar to having a cache miss here, this was the cache, this was the main memory, and this is the disk. Remember, we said that we want to have a majority of the time have a hit in the cache, but there could be some scenarios that we have a miss, so we have to go to the main memory. The same story happens for the main memory and the disk. The majority of the time you have a hit in the main memory, but in some very rare cases, you might not have that value that you want in the main memory, so you have to go and consult the disk. We usually call this a page fault, and operating system handles the page fault. So you have to wait for a huge amount of time, actually, in order of millisecond, for the data to be ready to be read from your disk and to bring back to the main memory, and then in some cases even it's going to be brought back to your cache. Okay, but this is actually being handled by most cases by the operating system. So this is just additional information of how do we know whether we have stored the value in the main memory or not. So we usually augment the page table with this 1-bit flag that says 0 or 1. We usually call it valid bit. So when we are requesting a specific address from the memory, during the address translation, we're going to check that whether this valid bit is equal to 0 or 1. If it's equal to 0, it means that it's not stored in the main memory. This results in a page fault. We have to go to the disk. If this is equal to 1, then it's not a page fault. It's already in the memory. We're going to go and bring it from the memory. Okay? So it's kind of like this is the story of our memory hierarchy, right? We have different delays between each of these levels. There's not something that we can avoid. We can try to minimize this miss, but at some cases, we're going to have a miss. We're going to have a miss when we are accessing different levels of cache. And then we're going to have different delays between accessing various levels of cache. We're going to have a different delays between accessing cache versus accessing memory. We're going to also have a separate delay for accessing memory versus accessing disk. And a user can measure this delays, basically. You can measure how long it takes for loading that value. And that's the key part for creating the attack that I'm going to just mention. Any question? All right, so this is kind of just to give you a full picture of how the address translation works. Usually all these things that I mentioned in the previous slides happens in this what's called a memory management unit or MMU. So the address, the virtual address comes here. It first asks a TLB to see whether they have the translation already or not. If the translation is there, we have the physical address, and then we go to the cache with the physical address. If it's not there, we need to go to the page table first. If the data is in the page table, then again, we have the physical address, we go to the cache. In some rare scenarios, the data is not even in the page table. In that case, it's a page fault. We have to go to the disk and break the data, right? So 3 different options. Either in the TLB, go to the cache. Either in the page table, go to the cache. Not in any of those, go to the disk, then go to the cache, okay? Okay, so now let's go back to the side channels. Any final question about how the memory hierarchy works? Cool. So remember we said that digital side channels is created because of the contention. Now we know that how the cache works. Let's see how cache side channel attack works. Okay. So in order to understand the cache side channel attack, let's say that there is a shared cache, and that's usually what's happens, especially at the lower level of cache, let's say L3. So L3 is like this huge cache that is shared among all the processes in the system in order to improve the utilization. So let's say we have 2 processes, process 1 and process 2. Process 1 is the adversary, process 2 is the victim, and they are sharing the same cache. And in this case, we are using a 4-way set associative cache. Okay, so it has 4 ways, and each line, we call it a set or a cache line, a cache row, sorry. So these are different sets. So for example, index 0, 0 goes here, index 0, 1 goes here, index 0, 2 goes, or 1, 0 goes here, and so on and so forth. But among each index, we have 4 different options because this is a 4-way set associative. All right. So now let's see what happens and how this attack works. So let's say that there is piece of code in this victim process that if the P is equal to 1, this victim going to access the cache. Let's say, for example, it's going to access this index 0, 0, right? So if its P is equal to 1, it's going to access this line here. And if its P is equal to 0, then it doesn't access that line, okay? Later on, I'm going to show you a piece of code that actually has exactly this characteristics. But for now, just assume that you have a piece of code that if P is equal to 1, we're going to access the cache. And if P is equal to 0, we're not going to access the cache. So that's on the victim side, right? So what the attacker wants to do eventually is figuring out the value of P. So the attacker wants to know whether P is equal to 0 or P is equal to 1. And we're going to show that by just accessing its own value, the adversary can exactly know whether P was equal to 0 or P was equal to 1. So let's see how. So the attacker going to use this this very creative 3-step approach that we're going to describe. But before that, just imagine one question that you might have is, why don't the attacker just directly access that line? So for example, let's say P is equal to 1, and the victim is actually putting that value in the cache, okay? So why don't the attacker just go and read this value? So this obviously is not possible because of the access control, right? Because the owner of this value is this process. So any other process that tries to read this will be blocked by the operating system. So you cannot obviously just access directly the content of the cache that it doesn't belong to you, because that violates the isolation property that we discussed, all right? So the operating system is going to handle that, yeah.
Here the attacker just wants to figure out if P is 1 or 0, or doesn't want to figure out the actual value of it.
No, just want to see whether P is equal to 1 or 0. But remember, we kind of indirectly use this. So if P is equal to 1, we're going to access the cache and we're going to write some content. We don't care about the actual content. We just know that there is some content by the victim process that's going to be written or read from the cache. Okay. So that's not a possibility, first of all. Let's see what is the possibility. Okay. So this, as I said, this is basically, if you go back to last lecture, I talked about the isolation as one of the key factors that we make the processor secure. So this is actually where the isolation can happen, right? But the story of the cache side channels is not actually violating the isolation in that case. It's actually much more sophisticated. So the attacker is going to use this algorithm that I'm just going to describe. The first thing that the adversary is going to do is that, let's say that the adversary knows that this set is the one that victim going to access. Okay, so the index equal to 0, 0. All right. So what the attacker first does is he or she gonna fill this cache set with all its own data. So basically, it just issue 4 consecutive loads A1, A2, A3, and A4. And we call this eviction set, which means that the adversary has found 4 different addresses that all of them maps into exactly the same index. And that's not a very complicated thing to do. The adversary can analyze the way that this cache is structured, find the indices, find the addresses that has this exact same indices. And since we have a 4 set associative cache, if we issue 4 nodes, the first one, the A1 gonna go here, the A2 gonna go here, the A3 gonna go here, and the A4 gonna go here. And since this is a four-way set associative cache, if we issue 4 consecutive loads, we're gonna evict everything and we're gonna kind of own the set. So in adversary perspective, after these 4 consecutive loads, the adversary just has replaced everything with its own data. So it has everything in the cache, that specific cache, right? So that's phase number 1. Then the attacker needs to wait to see what happens from the victim perspective. So remember, victim has 2 options. If the P is equal to 1, the victim gonna access the cache. If P is equal to 0, the victim is not gonna access the cache. So let's, for example, assume that P is equal to 1. So this is the case. In that case, the victim needs to access the cache. And remember, we said that the victim has to access index 0, 0. So what this access to the cache means? It means that the new data has to go into the cache. And since the cache is already full, we need to get rid of one of the existing content and replace it with the victim data. So we usually call this eviction. So we're going to evict one of these 4. There's different eviction algorithms that we're not going to talk about. Let's say we just randomly pick one of these 4 and we're going to evict it and going to replace it with P. So after the access of P1, this is how the cache will look like. The specific set we're going to look like, right? So this is the period of waiting for the victim to do some action, right? So that's phase number 2. Now we are starting the phase number 3. Now the attacker is going to scan this set one more time to see whether the victim has accessed the cache or not. How the adversary knows this information? It's basically going to re-access load A1, A2, A3, and A4. Okay, so going to issue the same set of loads. And what's going to happen is if all of these 4 contents is available in the cache, then the adversary is going to see 4 consecutive hits, right? If the victim has accessed the cache, it had replaced one of these 4. So the adversary is going to see hit, 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 and 1 miss, right? One of these 4 going to be a miss. We don't care which one, but we're going to know one of them will be a miss. So basically, if the attacker can somehow knows whether all four was a hit or three of them was a hit and one of them was a miss, the adversary now knows whether the victim has accessed this cache or not accessed this cache. So basically, if I tell you that this was the pattern, you can tell me that P was equal to 0. If I tell you that this was the pattern, you can tell that P was equal to 1, right? And you can repeat this over and over every time for every single bit of P. And by just looking at its own data, so remember, we never actually access directly what P is. We only access A1 to A4 two consecutive times during two different periods. We just know that whether this was a hit and whether this was a miss. I'm going to describe how we actually measure this time, but for now, just assume that we are able to know whether our access was a hit or our access was a miss.
Two questions. First, on the pyramid, if there's more than one miss, does that also count as P1?
So usually more than one miss doesn't happen because we are assuming that for this specific scenario, the victim only access that specific line one time, not multiple times.
Possibility of one.
Yeah, there could be noises that we're gonna discuss, but for now, let's assume that we are in the perfect scenario where either the victim or the adversary gonna access this cache set. If the victim gonna access this, it's gonna just fill it with one value and not multiple values.
So basically, the idea is that you, as an adversary, fill in the all four ways of cache with your own jump data.
Mhm.
Then you see if the victim accesses it, yeah, so you know that you can run your program.
Yes.
And then before this, like you said,
Wait a second, I cannot hear. Yeah, go ahead.
And I know you explained this like stage 2 and stage 3 of a cache cycle.
Mhm.
Can you explain the first stage again?
Yeah, the first stage is filling the cache with adversary's data. This is the normal, how it looks normally, right? So you have some random values, maybe you have A, you have P, you have A, you have many different things. So in order to start the attack, the adversary needs to reset this cache to some known state that it knows. And what does that is, it's actually accessing 4 consecutive values that the adversary has, as you said, with junk data, in order to make sure that this cache set is filled with the adversary's data. So all the ways in this set is filled with the adversary data. If it's, for example, 8-base sensitive, we have to issue 8. If it's 16, we have to issue 16. If it's 4, we have to issue 4.
So you fill it with the jump data first, and then you wait to see whether there's one miss or 0 miss.
Exactly. So you wait for the victim to take action. And if the victim accesses the cache, it has to replace your data. If it doesn't access the cache, then nothing will be replaced. So in that case, you will have 2 different possible scenarios. After the access of the victim, you're gonna either have a scenario like this, or you're gonna either have a scenario like this, right? So this means that P was equal to 1. This means that P was equal to 0. How do we know that? We're gonna issue A1 to A4 one more time. We're gonna measure the time it takes for loading this. If all of them are hits, it means that this is the scenario. If one of them is a miss, it means that this is this scenario.
Okay,
So now we
basically
can,
the adversary knows what the load time would be if all of them are hit.
yes,
And then just measures it and says, okay, if it's equal, then that means P equals 0. If
Yes.
the load time is more than the final load time, that's equal to 0.
exactly,
Because one of them is a miss, so you have to like go back to the main memory.
exactly.
So will this only work if the victim reads P and then there's a context switch to the attacker and then the attacker can fill the cache?
So this is usually a multi-core system. It's not single core. So you don't need a context switch. Usually the adversary would be on core number 1, for example, and the victim would be on core number 0. And remember, we're talking about, high-end systems such as cloud systems that has many different threads running at the same time. So yeah, so the only requirement is that the adversary needs to find that same physical computer that the victim is, run their application there. That's the only requirement.
But then the victim can't like read the value of P and then read the cache like before the adversary has any time to watch out the cache. Is that not possible?
So the whole thing needs to be very accurately timed by the adversary. So we usually call it prime phase, which is we need to fill the cache, then wait, and then probe, right? So, and then we need to repeat this over and over, right? So the adversary can find the time that what is the 2 consecutive wait time is, right? So what is the next time the adversary going to access the cache again? Because remember, for example, this is a piece of code that, for example, something like this on the victim side. It's just kind of like a for something if P load something, okay? So this would be basically the code that the victim is running right now. And it's gonna, consecutively gonna load things from base of the P. And, running each iteration takes T amount of time. The only thing that matters is that this value, this delay between this wait and this wait should be equal to T. And again, there is ways for knowing that as well for the adversary. You got a question?
So what exactly does the adversary accomplish by knowing that they have access to the cache?
So they know what the value of P is. So then after all of these, the adversary knows whether P is equal to 0 or P is equal to 1. And now think about that P is basically the key. So for example, if P is equal to 0, we access the cache. If P is equal to 1, we don't access the cache. So now we know what the key is.
So this only works if the attacker can determine a cache index that like his own data will conflict with the victim, right?
Yeah.
Could we like devise some sort of so I guess like randomization system where like if you XOR with the process bits or the bottom bits of the process or something, so that it's still like a one-to-one map, but that would make it more difficult for the attacker to determine which of his cache lines intersects with which of the victims.
Absolutely. And this is actually one of the ways of protecting against this attack. But still, the adversary can find the randomization. So if the adversary can reverse engineer the randomization algorithm, then it can find what exactly that index is.
So that would prevent, I guess, like a static analysis where you can't just like say, look at the victim's code and know, okay, I know he's going to access that. So it makes it more difficult because you have to dynamically determine.
Yes, exactly. So you not only need to profile the victim application, but you also need to profile or reverse engineer the mapping algorithm, whatever that is. And just keep in mind that the mapping algorithm to begin with is also not known. So it's proprietary, for example, for Intel processor or AMD processor and so on. It's not something that everybody knows how the mapping works, but there are algorithms that actually finds that for you. So to find that cache set, you need to have some pre-processing in order to find. We didn't talk about this here, but in reality, there is some pre-processing involved. And if you use some sort of randomization on top of that, you have to also reverse engineer that.
Okay. Yeah, I had a related question. I was wondering, how does the attacker even know that it's right to the cache, right to the same line as the victim?
Like how do you know which index it is and why P is equal to 0, for example, means
How does the values the attacker writes map to the same cache line as the victim?
So basically this attacks, so the general idea you got, right? So how this works in reality is we need to analyze the victim with the victim application and learn the pattern, the access pattern of its cache, okay? So what will happen is that the adversary first analyzes the victim application and finds a scenario at which there is a sensitive value, and depending on that sensitive value, we access a specific line in the cache. If it's not guaranteed that every single application has a scenario like that, But interestingly, for many critical applications, including this code that I'm showing here, which is part of the RSA encryption mechanism, there is a scenario like this, unfortunately, which means that there is a sensitive activity depending on the private key, the secret key of the RSA, that based off that, the application, the RSA encryption algorithm access the cache. And the adversary analyze this. This is kind of public knowledge because everybody knows what the algorithm of RSA is. They find the exact set that this is mapped to based off the discussion that we had. There is some reverse engineering involved, but we eventually can find it. That's not a big deal. And once we have that, then the story of the cache side channel attack basically. Does that make sense?
Yeah, just follow up on that. So would it not also depend on the hardware? Like if
Yes.
it's cache size will be.
Yes. For example, if it's like a four-way versus 16-way, that would be different. If the mapping is different, that might be different too. So it's hardware dependent of obviously, yes. But usually what you do is you find, so think about it this way, that you write an algorithm to find the eviction sets and to find that specific address and all those things. And you run this as a malware, for example, and this malware infiltrates to a specific computer. What you do is you first run your code to know what exactly is the characteristics of that hardware is. So for example, how many ways it has, what is the delay for hit and miss, and all those things. Once you have that, then you adjust your code accordingly. So it's more of like, think about this as a robot that goes into an unknown place. It's start doing some measurements first to know what exactly the environment is. And once it has that information, then it can launch the attack.
So in this situation, the vulnerability in the code is the decentralized.
Yeah, so the vulnerability is the code has some sort of if something sensitive and in accessing the cache based off that. So this is really the vulnerability.
Is it access or store? That's the.
It's the same thing, right? So load or store, in both cases, you might bring the data to the cache. So it's actually usually load, not store, because sometimes store just bypass the cache.
Right.
But yeah, usually reading from the cache. Yeah, load is the main issue. Any other questions? Okay, so let's take a quick break. We're gonna come back. We're gonna review it one more time, and then we're gonna move forward with the defenses. All right, let's continue. So let me again very quickly summarize how the cache side channel attack works. So the cache side channel attack works with a profiling phase. Which we analyze the victim code basically. You see there is a scenario that there is some sensitive value and there is an associated cache access to it or not. Then of course we need to profile the hardware to know the structure of mapping and structure of the cache. Once we know these two things, now we are ready to start the attack. The attack starts with the prime phase. We essentially fill the set with adversary data. all the ways in that set should be filled. Then we wait. Victim, access, or not, cache, set in other words. Then there is the pro phase, where we essentially, the adversary checks the hit, miss, pattern. Right? So that's how this works. And basically, this is going to be a repeat from 3. So this goes on and on and on to find all the information that's possible. Yeah.
What does it say in the wait phase and view access?
V is the victim.
Oh, either go.
So one final thing that I didn't mention is how the adversary knows that whether this is a hit or miss. Remember I described to you that if we access L1 versus L2 versus L3 versus memory versus disk, these are different access times. So the way that we measure this is that processors has these instructions, this timer instructions. For example, for x86, there's this RDTSC, which is basically this timer instruction that use a counter. So for example, you do RDTSC begin, you load A, and then RDTSC and then you just do begin minus end or end minus begin, and you see what time it is. Let's say this is time t. So during this profiling phase, you basically can find the times for L1, L2. We can find all these times, all right? And then basically we just measure this, we compare this with these known times, and we can easily know where the data is stored. So in most cases, assuming that the victim data is not stored in the cache at all, what we need to know is that whether it's L3 hit or whether it's L3 miss. Basically the hit time of main memory versus the hit time of L3. That's the only thing that we need to know. In some other cases, it might be difference between L3 and L1. But generally, the idea is that we need to be able to measure the time and have two separate cases, whether it's in the cache or not in the cache, and then just approximately measure that time and say whether this is which scenario it is. Okay, and accessing a timer and having a timer, unfortunately, is very easy in processors. In most cases, as I said, this specific instruction is actually giving you that information. But there are some other cases that you don't necessarily want to use this instruction. There are other ways, like using a for loop and a counter to measure that time. There are very multiple ways of creating a timer inside your assembly code. If you're interested, you probably can read the papers relevant to it. But it's very feasible to actually create this timer in your code. Okay? Does that make sense? Awesome. So as I said, this is actually very quite realistic, and there are lots of real world attacks. One example is this RSA code, the exponent part of the RSA code, which actually using this EI, which is part of the exponent, which is actually part of the secret key. That depends on that. We either access this cache or not accessing this cache, and that's usually creates the problem. Okay. There is another way of using cache such. Yeah.
For the algorithm, the exponent one. Is it like the same idea as before, but we're doing? I don't really get the idea.
Get idea of.
Like, what are we doing?
So this is RP. So if P is equal to 1, then we run this if statement. If P is not equal to 1, then I'm going to skip this. And as you can see, there is this part which is actually accessing to the cache. Okay, so yeah, E is basically our P in our example in some sense. Another possible way of using cache side channels is actually for machine learning. Remember, we talked about model extraction. People actually found that the cache pattern and access pattern of a machine learning model is basically actually depends on the structure of the model, like how many layers we have, what's the size of the layers, and so on. And basically using the cache side channel, we can find that structure. So there's a large class of attacks for model extraction that use digital side channels, including cache side channels, to find that information. Okay, so instead of like querying the system and then tries to build a model, they actually looking at the side channel pattern of the cache, and based off that, they're trying to learn whether, for example, this is 4 layer, this is 5 layer, how many neurons exist in each layer, and so on, right? If you're interested, there's this interesting paper that you can take a look to understand how it works. There are multiple other papers actually in the same domain as well that tries to use this. Okay. And the one that I described to you was called prime and probe, but there's actually multiple other variants of cache side channels as well. There's flush and reload, there's flush, take away, streamline, etc., etc. In all of these, the way that we create our eviction set and the way that we measure it is slightly different. But the general idea is the adversary creates a pattern and waits for the victim to access or not access the cache. And based off that activity, the adversary infers whether this value was 0 or not. How do we set this up and how do we read the value off of the victim? Depends on one attack to another attack. The prime and probe is the most popular and most famous one, but there's many other ways of doing the same thing as well. So just keep in mind that the prime and probe is not the only way of conducting a cache side channel attack. Okay? So is cache the only channel for digital side channel? And the answer is unfortunately no. Essentially, any shared resource between the adversary and the victim can be attacked. Not necessarily the same way for the cache side channel, but you kind of get the idea, right? So the attacker creates some pattern, right? It waits for the adversary to impact on this pattern. So the pattern might be the exact same thing or something different. And the adversary basically reads that or scan that and then infer the information about the victim, right? So we kind of like think about it that we create some sort of a trap for the victim. We wait for the victim to interact with that trap. And based off that interaction, we infer the information. All right. So the cache side channel was one of the examples. The trap in the cache side channel was creating this eviction set and waiting for the victim to actually evict something from that eviction set. There are others, for example, for TLB, you can use this. For branch predictor, you can use this. For prefetcher, you can use this, and so on and so forth. So in all of those cases, you kind of like create some sort of known pattern, wait for the victim to interact with that pattern and see what victim has done. And based off that, you infer that information. And the most important thing about this is that you never actually directly access the information that is owned by the victim. You always look at your own data and your own pattern. And the only thing that you use in order to infer this was the interaction between the victim and your pattern. And that's the key idea in digital side channels. Okay. So these are the other examples. So for example, GPUs can be used for side channel attacks. TLBs can be used for side channels attacks, DRAM can be used for side channel attacks, branches can be used for side channels attacks, etc., etc. If you're interested to know more about this, you can maybe quickly take a look at these papers. So now let's actually talk about the defenses, that what we can do in order to defeat this guy side channel attacks. Similar to any other attack defense scenarios that we talked about, this is not something that is fully solved, and it's also a continuous cycle between the attacker and the defenders. So let's actually talk about multiple defense mechanisms. The first one is based on what's called, we call it software or compiler-based solutions. So remember, the reason that we have this attack is that we have some if P and then do something, and then else P and not doing that, right? So skipping that. So basically accessing data here is the reason for the cache sidechain. So one easy fix to this problem is, how about regardless of the value of the P, we always access the cache, for example, right? We always do the exact same thing, no matter what the P is. As this part is the part that we care about. This part is basically junk and redundant activities that we do. But this means that the adversary never infers any useful information from the system, because regardless of P equal to 0 or P equal to 1, we issue a load to the cache. So that's basically very useful and very effective in defeating the cache side channels and generally side channels. The problem with that is that now you're taking much more long. You're always paying the worst case scenario for your code, right? Because if you do the else and the if always, it means that the amount of instruction that you execute includes both of them. Versus in reality, you either execute the if statement or the else statement, and you never do the both. So this means that the performance hits significantly. So the performance degrades significantly because you are executing additional instructions that you don't want to, and your code size also increases because you're just adding redundant code for every single if then else statement. So it fixed the issue mostly, but it comes with some penalties, including the performance, which unfortunately this is usually the main roadblocker, because your code would be very slow when you do something like this. And how you do it, you can either do it using the software. So when you're actually writing the code, you can proactively create this, or you can ask the compiler to do this for you. So the compiler basically detects this conditional statements and just pad the code with the other part of these statements. Okay, there are some examples for this if you're interested to read more. So that's the number one defense. The second defense is basically what's called isolation or partitioning. So remember, we said that generally the reason that we are saying this is that we're sharing the same set between multiple processes, right? So for example, the adversary can fill this set, the victim can also access this set, right? So what we can do is that we can partition the cache either in vertical dimension or in horizontal dimension. So for example, we can say that, okay, only even ways can be accessed by process number 1, odd ways can be accessed with process number 2. In this case, we never physically share the cache really, right? You only, as the adversary, you can only access some of the ways, and the victim can only access the other ways. And you never know what's going on with the other process, right? This is kind of solve the issue, but on the other hand means that you're basically underutilizing your cache significantly. Think about a scenario where P1 and P2 are not adversarial processes, and for some reason P2 does not want to use the cache at all. So in that case, the effective area for your P1 would be only 50% of the cache, versus in normal scenario, P1 could have just used the entire cache, right? So again, you take a performance hit just because you're not fully sharing your cache. You're only, dividing this statically, and you don't give all the space to your cache, right? So, but this again fixes the problem because you're physically separating your cache between multiple processes. So good for security, not great for performance. And again, because of that, it's not a popular scenario because performance is usually the main target for our systems. Does that make sense? Any questions here? The third option is randomization, as one of you suggested, right? So how about making it difficult for the adversary to know what's going on with the victim code? To maybe just randomizing the access patterns of the victim, maybe randomizing the way that the cache is mapped, maybe adding some additional noise to the victim. All of these options are possible.
Is this not just security, but obscurity?
You can actually share the randomness algorithm. That's not an issue, as long as it's the randomness is kind of not deterministic. That should be fine. But I agree with you that could be an issue. This is security by obscurity in some sense, and this is that's why it's mainly can be reverse engineered by the attacker and can be circumvented. Yes. Another possibility is monitoring. So basically, we don't prevent, but we detect that an attack like this is happening. How do we detect it? So given that there is some known pattern for this attacks, first the attacker needs to fill the cache, then it has to wait, then it has to access it again. There's kind of like very known and deterministic pattern the way that the attacker attacks the system. So how about we kind of like monitor this and try to detect it? There are some efforts in detecting this, and they have been quite successful. Two problems with it. One is there are lots of false positives, which means that there are some other legitimate applications that looks very similar to this. They just, for example, they go through the same array over and over, things like that. So the detection can detect the attack, but also unfortunately flags lots of legitimate applications as a potential attacks as well. The second thing is an after the fact in some sense, right? So some information is leaked already before we actually even be able to detect it. So in some very sensitive scenarios, this is not the best solution, but still a possibility. There are many other scenarios as well. These are the main ones that I described here. This is very active area of research, actually. There are lots of papers both on the attack side and on the defense sides these days. So every year there's a large group of new defenses and new attacks. But the key outcome and the key takeaway is that because of the sharing, unfortunately, we have this scenario, and this attack has not been fully removed, same as the other attacks that we have discussed in the class. There is the new type of attacks that the adversary can do, and that way they can circumvent, for example, the randomization, they can circumvent the detection and all those things. Okay. But of course, there is both for the attack and defense, there are some challenges. Feasibility, accuracy, overhead these are the main challenges specifically for defense. I already discussed this. So you can, for example, you always have the option of not using the cache at all, right? So if you don't use the cache, if you remove the cache completely, then you never have the cache side channel problem as well, right? Or you can completely get rid of your computer and you don't have any digital side channel problem, right? So you can always get rid of some of these features, and by getting rid of those features, you will have a much more secure system. But this is the game that we have always been start playing, right? So we want more convenience. We want better systems, better services. We want more features, and because of that, we are introducing these new vulnerabilities, right? The moment that we start, adding a smart device into our home, we are opening the chance of a cyber attacks to that device as well. But on the other hand, the convenience that that smart home device, for example, gives us, kind of justified, right? So it's kind of like the game that we need to be aware. Ideally, we want to be able to use that device, use that feature, use that functionality without paying the price of the security. But unfortunately, these moments is not something, it's still a trade-off between security and usability. And we are trying to move to that direction that we can actually have a system that is secure and also gives us the features that we want, okay? Okay, so that's the story of cache side channels and generally digital side channels. Any questions about this part so far? Okay, so something that is very relevant to side channels is what's called covert channel. So covert channel is basically this communication strategy, this communication protocols between two parties. And it's covert, which means that it's supposed to be, so these two parties are not supposed to talk to each other, all right? So they find a way, a secretive way to communicating to each other, all right? So why do we need covert communication? So let's basically go with this example here. That, remember we said that we have the principle of list privilege, right? So for example, we say that we have one process, process number one, and process number two. And process number one, for example, has access to the camera because it's maybe a photo editing app, but it doesn't have access to the network. And process number two has access to the network. Let's say this is like a message, message app. So it has access to the network, but it doesn't need to have access to the camera, right? And we kind of both of them are secure. So your photos are kind of secure, or your camera is kind of secure because this app that has access to the camera can never send the information out. This other app that has access to the network does not have access to the camera. So if these are the only two applications in your system, your camera is somehow secure, even if this one is compromised and even if this one is compromised. If both of them are compromised, your camera is secure, right? So now the covert communication is basically saying that what if these two processes can collude with each other, can collaborate with each other, and this one can maybe send the information to this one, the camera information, the photo information to this one, using some sort of a covert communication. Why it has to be covert? Because if they use the normal ways of communication, the operating system will caught it, right? So if this process tries to send the information to the other process, it has to go through the operating system. And of course, operating system will caught this as an anomaly, right? So we want to find a way inside our system to be able to communicate between processes to send out some information to break this list privilege, for example, principle of list privilege, right? So that's the idea of what we want to achieve. And interestingly, we can actually use, for example, cache side channels to create this covert channel. How do we do it? So let's say, again, back to process one and process two. The way that we're going to send this information is using the cache. So let's say there is a set that has 4 different phases. Let's say in the offline phase, P1 and P2 agrees on set X, and this is set X. So they said, both of them, that we're going to use this specific address. What we're going to do is that in order to send the information, P1 and P2 agrees on a specific protocol, right? So what is that protocol? For cache side channel, the protocol is very interesting. So the P1 says that, so P1 is the transmitter and P2 is the receiver. So P1, let's say, is the one that has the data from the camera, and it wants to send it to the P2, which is access to the network, and it can send it to the open world. So P1 is going to say that, let's say I want to send zeros and ones. Let's like a Morse code, right? If I want to send 0, what I'm going to do is I'm going to access the cache. If I want to send 1, I'm going to not access the cache, all right? And by cache means this specific step. And we already know how an adversary can find this information, right? P2, what the P2 going to do is that we're going to do A1 P2, A2 P2, right? It's going to fill the cache with this 4 data. So prime phase. It's going to wait for P1. And if P1 wants to send 0, it's going to evict one of these values. Oops. It's going to evict one of these values and just fill it with some dummy value. If the value that P1 wants to send is 1, it's not going to evict anything. Then time comes for the probe phase for P2. And it's going to go through the cache and see whether there's a miss or all of them are hit. If all of them are hit, means that the original value that was supposed to be sent was 1. If there is a miss, it means that the value was 0. And then they can repeat this over and over again to send all the bits that they want. And again, they're not using any communication channel using the operating system. They're directly talking to each other, but just accessing the cache, accessing the memory. And they already come up with the protocol phase beforehand on the offline phase. And they can now talk to each other over the cache. And they can talk very quickly, right? So they can within milliseconds, they can send lots of bits. And each bit is basically this simple protocol. Does that make sense?
Is the bit a set in its entirety, or is it a data point in the set? So like in this situation, would the output be 0, 1, 1, or would it just be 0?
No, it will be just 0. Okay. Yeah. So remember, we cannot directly send information to each other because we don't share any address.
Right.
And any address that we want to share, the operating system will catch us. So we need to come up with this scenario. Obviously, there are methods to optimize this. For example, let's say sending 2 bits per each access and so on. But the very basic and bare minimum one is you just access or not access the cache, and that sends 1 bit. And then you can repeat this.
Okay.
So so all these steps are exactly the same as the cache side channel, but this time we are intentionally access the cache. So remember, previously we had the victim that had no idea about this possible attack. We just wait for the victim to access the cache. This time we are saying that P1, which is replacing the victim, is actually a culprit. It's actually colluding with P2 in this case. So P1 actually intentionally accessed the cache at that specific address, whatever that address is. So exactly similar algorithm. Prime means that the P2 has filled the cache with all its own data. It's going to wait for P1 to access the cache or not accessing the cache.
P1's like the victim, P2 like the.
Yeah, exactly. And
what's the difference between that and the cache side channel?
so the goal is different, right? So cache side channel, you're trying to steal some information from the victim. For a covert channel, you're trying to communicate between the 2 processes. Okay. So
like securely communicate without having like interference from a third adversary.
no, not securely. You're covertly communicating. So back into here, here's the scenario. You have 2 adversarial processes, P1 and P2. The goal is extracting the photo from your camera to the outside world. But because that the OS is kind of controlling this, it doesn't allow you to access to the camera and network in the same application, okay? So either your process has access to the camera or it has access to the network, okay? So P1 has access to the camera, so it has access to the data that we want to exfiltrate. And P2 has the network, which means that it has the communication platform to send it out. So we need to find a way between these two to communicate to each other so that P2 gets the data, and then now the data can be extracted to the outside world. And as I said, since the operating system is controlling everything, you cannot just simply send a message from one process to another process, because that's a system call, has to go through the operating system, and operating system obviously blocks this.
Oh, okay, so like you're basically as an adversary, you're controlling both.
Yeah, exactly. Both of them are closing together. Just one adversary that's controlling two processes.
Okay, that's how the adversary of the combination of both P and P2 with the adversary.
Yes, exactly. And this is still under the principle of least privilege, still under a very sophisticated operating system that is completely secure, but we still manage to extract the information using this thing. Okay. So that's the example of the covert channel, and the covert channel is useful. And cache side-channels is not the only way of creating a covert channel. Any other digital side channels that you can think of can also use for a covert channel as well. So for example, people have shown that GPUs can be used for covert channels, TLB can be used for covert channel, etc., etc. Right? Are we good? All right, so the final thing about digital side channels, I'm going to very quickly go over it and then leave the rest of the definitions for the next lecture. And the last one is what's called a transient side channels or transient execution side channels. So this is actually a very new side channel attacks. And the way it works, so probably most of you have heard about Spectre and Meltdown. So this is the general term for these attacks is transient execution attacks. And the way this works is that the way that your processor, your modern processor works, and actually there are some design bugs that these people have found those design bugs, and they use it to break the isolation assumptions that we have. Okay, in order to understand how this works, so eventually what the transient execution attack does, it allows you to access illegal memory lines. So remember we said that there are P1 and P2, and you have the memory, you have P1 and P2, and if P1 tries to access something in P2, the operating system will block it. In transient execution attacks, specifically Spectre that we're going to describe, we're going to give you an example, a possible scenario that P1 can actually directly access content of P2. And this is basically some sort of a design bug that exists in the hardware. And this is usually used, this feature in modern processor called speculation. I'm going to describe what a speculation is for those of you who don't know. And the adversary going to use this speculation in order to access the content of the memory. So at the end of the day, what would happen as the outcome of this attack is that adversary, which is in this case process number one, gonna exploit this bug in a speculation in order to be able to attack any arbitrary line in the address line of process number two. And that's a huge, huge problem, because we are assuming that process number one cannot read anything from process number two, but with this bug, we can actually able to read things that we want to read from process number two. All right. So in order to understand this, we need to first, again, have another detour of computer architecture and learn what this speculation is. And we need to focus on the processor this time, because speculation is an optimization feature in the processor. Since we don't have much time, I'm going to pause here. And then in the next lecture, I'm going to quickly go over what is the speculation and how the speculation can be exploited in order to launch a transient execution attack. And afterwards, we're gonna switch to physical side channels attacks. It's another candidate for attacking the systems. All right, so that would be what we're gonna do next. All right, guys, thank you.